and welcome to this lecture on vehicle routing problem. So in our previous lecture, we focused on the formulation of a traveling salesman problem, and it is an interesting problem. However, the TSP has certain limitations. What are they? The first is that there is no capacity enforced on how much the salesman can carry when he is traveling to the different nodes, right? So there is no capacity restrictions of any sort. The second is that we consider only one traveling salesman, and that one salesman must visit all the nodes and come back to the starting point. The third, there could be any starting point. Given 10 nodes, I could have any of the 10 nodes as my starting point. The only constraint is that I should return back to the same thing. So when we are specified a specific set or a specific location from we have to start, and if we are given multiple salesmen or multiple vehicles, and if there are capacities on that vehicle, then we enter into the space called the vehicle routing problem. So we are basically extending the TSP to solve these constraints. And when we are extending the TSP to the vehicle routing problem, there are several variations that are possible. One such variation is the single depot vehicle routing problem, the most simplest form of VRP. So in this, what we say, we have a specific depot where all the vehicles are present. There are several customers who are present. They are the nodes, right? And each node has certain amount of requirement, the demand at that node. The vehicles present in the depot have a particular amount of capacity, and there are a fixed number of vehicles. And these fixed number of vehicles having these capacities must visit all the nodes or must satisfy the demands of all the nodes, right? We are also provided the distance. Just like in our TSP problem, we have a distance matrix here. The only difference being, in the TSP problem, we had n customers, so an n by n matrix. Here, we have n customers and one depot, so the distance matrix would be n plus 1 by n plus 1, right? So there will be n customer nodes and the depot, and we will know the distance between the different customer nodes and the distance between the depot and the different customers. So that is the problem. And the most important thing here is that we have a depot. All the vehicles are at the depot, so all vehicles must start from the depot and must finish at the depot. Unlike the traveling salesman problem, where the starting point could be anything, and based on that starting point that you choose, the ending point must also be the same. But here, the starting point is also specified and the ending point is also specified. So that is a single depot vehicle routing problem. And intuitively, just for the sake of completeness, this single depot vehicle routing problem can actually be extended to the multiple depot vehicle routing problem, where you have multiple depots, basically multiple points where different vehicles are present, and there are different customer segments, and these customers can be satisfied from vehicles in any of these depots, right? And most intuitively, this multi-depot vehicle routing problem can actually be seen in your road transportation. So if you are from Tamil Nadu, you will know that there are several bus depots in the city, and the vehicles in these depots would be stopped there, and they will start from that place. But it is very interesting to note that, let's say a vehicle is starting from a location called Tiruvamur, it need not be stationed at Tiruvamur. It will be parked in a different location called Adyar. In the morning from Adyar, it will go to Tiruvamur, and from there the route starts. So that is basically a version of a multi-depot vehicle routing problem. Where should I park my different vehicles which travel on different routes, right? So that is a case of a multiple depot vehicle routing problem. But in our discussion for this particular session, we will be looking only at the single depot vehicle routing problem, the simplest version of it. And again, we will look at the formulation of this vehicle, a single depot vehicle routing problem. There is something very interesting in a simple depot vehicle routing problem. For this same problem configuration, we can have three types of problems, right? The first one is where we look at all the vehicles that are available to me, they must be used, which means every vehicle that I have must at least visit one node and come back. That could be a requirement for me. So that could be one formulation that I can do. The second formulation, I must satisfy all my demand but using minimum number of vehicles. That could be the second. The third is an extension of 1 and 2 where I say I must use minimum number of vehicles, but I must also travel minimum distance. So as much as possible use minimum number of vehicles, but also make sure that the distance traveled by my vehicles is minimum. So that could be another problem. And again, for our discussions, these are different variations or types of the single depot vehicle routing problem. We will look at the first scenario where we say all the vehicles that I have must be used. I have a resource, I will use it to the maximum. So that could be the scenario, right? So what we would do is we will formulate this problem. And again, when we are looking at the formulation of single depot vehicle routing problem, there are several formulations that are available. The formulation I would be discussing now was given by Actem and Kaket in 1991, and the paper is provided to you. So if you are interested, do go read it. And in this formulation, like I said, we are going to use all the vehicles that are available and try to get to a route for everything that is there. Like our TSP, we will start off with a verbal formulation where we would first define our sets, our decision variables, our objective function, and the constraints. First, the sets and parameters. We have nodes. So, and we are going from one node to the other. So, we might have a set from set I, set j, which is from 1 to n, the different customers. We will also usually have a point 0, which would represent the depot. So, the set could actually be represented as 0, 1, 2, so on up to n, such that 0 represents my depot. So we have a n plus 1 by n plus 1 matrix. And for this, dij is the distance between node I and node j, right? And like I said before, dii would be set to a very, very high number so that we avoid assignment of a vehicle to the same location. x11 would be 0, right? Apart from these two, the remaining 3 sets or parameters that are defined to you are specific for the VRP. They will not be present in your TSP. The first is the set V, which is the set of vehicles that I have. So let's say I have k vehicles with me. So we would go from 1 to k, vehicle 1, vehicle 2, vehicle 3 up to vehicle k. Qj is the demand that I have at node 1. This was not relevant for me in the TSP because I do not have any capacity constraints. But here, since I have a capacity constraint, I must know what is the demand at a particular node. So Qj, the parameter I should know, and W, which is the capacity of my vehicle. And for this formulation, I assume that all vehicles have the same capacity. So W is the capacity for every given vehicle. Okay, so these are the sets and parameters that I would require for formulating the single depot vehicle routing problem. Next is the decision variables. My decision variables for this problem is exactly same as my TPS. That is why it's an extension of my TPS. So we are adding more sets and parameters, but our decision variables are the same. So we have xij, which is 1 if I go from node I to node j immediately, 0 otherwise, and ui is the auxiliary variable that I'm going to use for eliminating subtours in the case of TSP for ensuring capacity here. In this particular formulation, the UI which was used for eliminating subtours in my TPS would be used for ensuring the capacities of the different vehicles. We will discuss that when the appropriate constraint is being explained to you. Next, the objective function. I have only told you that I have to use all the vehicles. So the objective can be, I want to minimize the distance while using all the vehicles. So the objective function is to minimize the total distance that I am traveling when using the different vehicles. So that is the objective. Now, since this is an extension of our TPS and the objective is exactly the same, the formulation of the objective is also the same. So I'm not going to repeat myself. I will just put it out there for you. It is going to be summation over I, summation over j, dij into xij. So this would be the mathematical representation of the objective function for the VRP. It is the same thing as the case of the TPS. Okay, so TSP, traveling salesman problem. Having said that, let's now go to the constraints that are present for me in the VRP problem. So the first constraint is that every node must be reached either from the depot or from another node, right? I have a depot as my starting point, so all the vehicles must start from there, or they must have been in a location, and from that location they should go to a different thing, right? It's basically telling this constraint, in a sense, is basically telling all the vehicles must start from zero. The second thing is that all the vehicles must come back to the starting point, and their starting point is always going to be zero. So if a vehicle is in a different location, from that location they should either go to a different location or they must come back to zero. So constraints 1 and 2 are basically going to enforce the requirement that all vehicles start from a location which is zero, and all vehicles end at the same location which is again zero. So that is basically constraints 1 and constraints 2. The third constraint is that there are exactly V routes. Since we have V vehicles, we must ensure that there are V routes. Every vehicle is assigned to at least one node. So that is the third constraint. The fourth constraint, we have a vehicle, we have its capacity requirements. So the capacity of a given route must always be met, right? Must always be met, and when we are meeting the capacity, it should not exceed the vehicle capacity of that particular route. So that is number 4. And the fifth one is a non-negativity, which is our binary variables. Our xij must be binary in nature, and our ui must be an integer, must be a positive number. So this is the verbal formulation of the VRP. Now let's get into the mathematical formulation. First, every node must be reached either from the depot or from another node. So what does that mean? So let's look at the standard example. We are always taking the 5 city case example. So we have node 1, node 2, node 3, node 4 and node 5. And of course, we also have the node 0, which is our depot. Right. Let's say we take node 1. What does that mean? If I have to go to node 1, I must either go from 2 to 1, or from 3 to 1, or from 4 to 1, or from 5 to 1, or I must have had it as my starting node and gone from 0 to 1. That is my constraint. So how do I ensure this? I ensure this by saying either 0 to 1, or 2 to 1, or 3 to 1, or plus or 4 to 1, or 5 to 1 is equal to 1. And all of these are binary variables. They can either take a value of 1 or take a value of 0, right? So if one of them takes a value of 1, everything else will be assigned 0. So the constraint is met that when we are reaching a node, the end point of the node is either from another node or from the depot. So the vehicle will always start from the depot or from some other node. Let's go to the next constraint, which enforces that the destination should also be a node or the depot. Again, the 5 scenario case, 1, 2, 3, 4, 5, and if we have 0 from, and if let's say I am at 1, from 1 I can either go to 2, I can go to 3, I can go to 0, I can go to 4, or I can go to, I can go to 4 or I can go to 5, right? So x 1 to 2, x 1 to 3, x 1 to 4, x 1 to 5, and x 1 to 0, one of them must be 1 and all others must be 0. So from a location, I can go to another location or the depot only, right? And if you just extend this, you will understand why it will enforce that every location will start with 0 and end with 1, end with 0. That I will leave it as a self work for you guys to just explore a bit. But these two constraints will ensure that every vehicle starts at the depot and ends at the depot. Okay. So these are the first two constraints. The third constraint, if I have V vehicles, I must use all the V vehicles, right? So that is basically meaning I must have all the vehicles starting from 0 and I must have all the vehicles ending at 0, and the sum of these must be equal to V. So if I go from 1 to 0, if I go from 2 to 0, if I go from 3 to 0, if I go from 4 to 0, if I go from 5 to 0, this must be equal to v. Similarly, if I come from some location, if I, I think I wrote the other way around. If I go from 1 to 0, right? Yeah. If I start from 0, I must go to one of the other locations, right? 0 to 2, 0 to 3, 0 to 4, and 0 to 5. And whenever I start from the depot, I must have 5 vehicles leaving it. And if I have 5 vehicles leaving it, I should have 5 vehicles coming back in, provided I have 5 vehicles, right? So this is that constraint. I will ensure that all my vehicles, V vehicles, are utilized by me for the 5 city problem, for example, right? So next, let's look at the most interesting piece in the vehicle routing problem, which is the capacity constraint. And this constraint would be very, very similar to your subroute elimination constraints of the TPS when you look at it. And let's try to understand this constraint through the eyes of an example. So I have 5 locations. So I have location 1, location 2, location 3, location 4, location 5, and the depot which is at 0. Let's say I have a route which goes from 0 to 1, 1 to 2, and 2 back to 0. And in this case, and the second route, let's say, goes from 0 to 3, 3 to 4, 4 to 5, and 5 to 0. So those are the 2 routes for me. I have 2 vehicles, I have created 2 routes. Now I must ensure that when a vehicle goes from 0 to 1, 1 to 2, and 2 to 0, the capacity of 1 and 2 put together is less than the capacity of the vehicle, right? So that is what I should ensure. How is that made? So if we take a route, let's write the constraints equations for based on this formulation and see whether it is ensuring my capacity. So I go from 0 to 1, and that is going to be W into X 0 to 1 less than or equal to W minus Q1. J is 1. Similarly, I go from 1 to 2, W X 1 to 2 less than or equal to W minus Q2. Then from 2 I go back to 0 plus W into X 2 to 0 less than or equal to W minus Q0. The most important thing, this is source, this is destination. All right. So what happens if I vertically add all of these? Cancelled, I will end up with U source minus U destination plus 1, 2, 3, because all of these are ones. So 1, 2, 3, 3 times W must be less than or equal to 1, 2, 3, 3 times W minus Q1 minus Q2 minus Q0, and Q0 is 0. There is no demand at my depot. And what do we have here? U depot is destination minus U depot is source is W, right? So U depot is destination minus U depot is source is W. Here it is inverted. So minus W plus 3 times W must be less than or equal to 3 times W minus Q1 minus Q2 minus Q0, which is 0. That is what we have. So basically, what does this translate to? Q1 plus Q2 must be less than or equal to W when the route is followed. So the total load that I carry must be less than or equal to the vehicle capacity that I have. So this is how this specific constraint ensures that my route that a vehicle takes meets the capacity of that particular vehicle. All right. So this is the capacity constraint. And finally, we have the non-negativity constraint, which says that our decision variable is binary. And of course, we always have, I believe I missed it here, ui must be greater than or equal to 0. So that is our constraint. So with this, we come to the conclusion of the vehicle routing problem and also the conclusion of this week. We would be looking at the formulation of this in Python, or the tool where this would be coded for solving. That would be Python, and the Python code is provided to you. So do run that for the data set that is given and see how the solutions are generated. Thank you.